I'll wait for it to go to 11:01, Amy, and I will not take that time away from you, I promise.
I'm not worried. I can always talk faster.
That's my style. We can fit it in.
Well, good morning, everyone. Welcome to this second day of the AI4ESP workshop. I hope everyone is well rested and with a thirsty mind. We are beginning this morning with two invited plenary presentations. The first speaker is Professor Amy McGovern, who is the Lloyd G. and Joyce Austin Presidential Professor of Computer Science at Oklahoma University. Amy got her Bachelor of Science from the Carnegie Mellon University and a PhD from the University of Massachusetts in Amherst. And as a personal point of view, I have mainly interacted with Amy through the American Meteorological Society, where she has been very active in shepherding the committee for the application of AI. And I very, very much enjoyed that interaction, and I am looking forward to her presentation today. Amy, over to you.
Thank you. I would only add one thing. I'm not sure where you read that from, but I'm also jointly appointed in School of Meteorology.
Aha.
Okay. So hopefully we get PowerPoint to behave and we start. Okay, I'm assuming that everybody can see the correct screen. And I'm going to move the window full of people off to the other monitor. Okay, so I asked Nikki especially what she wanted to hear about, and then her response was she wanted to hear about what I was excited about as well as grand challenges. So I tried to combine those two. And so what I'm going to talk about is a focused set of ideas for the beginning part of this about the grand challenges for trustworthy AI for machine learning, trustworthy AI machine learning for Earth System Predictability. And then for the second part, I'm going to talk a bit about what we're doing at our NSFAI Institute, because that is what we're focused on. So if PowerPoint behaves and it advances my slides, the next two slides actually come straight from the talk we also gave at the NOAA workshop. This was a joint talk with myself and Jason Hickey. And this quote, I don't know if Peter Dubin is actually online too, but this quote came straight from Peter Dubin's report on the future of AI and ML for weather, water, and climate. And I really like it. And it speaks to what we were thinking about. If we're trying to think about grand challenges and we're trying to think about where we're going to be 5 years and 10 years, which is what we're supposed to be doing in the breakout sessions, we need to think about, what else has already been done. And this, I really love this quote. We anticipate that it will be increasingly difficult to distinguish between scientists working on machine learning and domain scientists in the future. And it will be no longer possible to identify the tools that were originally targeted for machine learning applications in 10 years. And that to me is a really, really visionary quote. And in our talk that we gave earlier, just a month ago, we talked about how the US Weather, Water, and Climate Enterprise can achieve this, because this was done at ECMWF. For here, I'm not necessarily going to focus on that. I wanted to focus on the second part of what Jason and I talked about, which was the Decadal Vision. And I specifically bolded some words because I want to talk about them, because I think that they focus a lot on the aspect of what we can talk about for grand challenges for trust. So we wrote up a sort of a decadal vision for the US version of this, that in 10 years, AI and machine learning will be fully integrated into weather, water, and climate. It'll span from foundational research all the way to operations. And, we have pieces in each part of this right now, but it is definitely not fully integrated. It's not seamless at all. Seamless is a word that was used yesterday in one of the breakout sessions that I was running. AI and machine learning will revolutionize our scientific understanding. And that's something that we're just beginning to be. We're right on the tip of the iceberg on it, I think. By facilitating exploration and creation of large, detailed, accurate models. And I grabbed a picture of the digital twin for that, because I think it is a phenomenal example of a large, detailed, accurate model that will be available when it's ready. They're going to represent a wide variety of weather, water, and climate phenomena. That AI and machine learning will be seamlessly integrated into forecasting at all scales. And I mean that so that you're going all the way from the micro scale. Just read a fascinating paper about doing really micro scale forecasting at like the farmer field level, all the way out to the global scale. And it will facilitate scientific discovery and forecast improvements at all those scales. And then I want to talk some about the second paragraph too, before we get to the ideas of the grand challenges. By creating a fully connected system capable of integrating global scale data, we will transform humanity's relationship. And that's one of the key things. I think the first paragraph that we talked about in our vision is a lot of technical part. The second paragraph, we talk more about the people part, because I think the humanity part really matters. We can't just create new AI and throw it over the fence and expect that it's going to be used. And we can't just create new AI and expect that it's going to solve everything in the world. We have to deal with humanity as well. And by creating a seamless system that can do data at all different scales, we really want to be able to transform humanity's relationship with the world around us. Scientists can seamlessly gather observations and blend them into the models at all scales, and that innovators can create personalized predictions, facilitating decision-making from the individual to the corporate level. And these are all made possible through collaborations with social scientists to improve the understanding of what's going on inside the humans, the decision-making and the communication. And I think those are all really, really key. Which brings me to the question I asked, which is first of all, what do all the highlighted phrases have in common? I had a bunch of those things in bold, and I just grabbed them over on this slide. Fully integrated, revolutionize our understanding, seamlessly integrate into all scales, transform our relationship, and have personalized predictions. I see two halves of these, and they both involve trust, which is what I said I was going to focus on, that we were going to talk about grand challenges for trust. So the first half is the scientific end users. They fully need to trust the AI and machine learning and use it seamlessly across all scales of their research and their prediction. And then the second half is talking about all kinds of end users, the end users that range from the general public to the scientific end users. They trust and they use AI and ML in a wide variety of situations. And this includes life or death situations. For example, you don't just want to make an AI method that it works when the weather is sunny. Like I'm glad it's predicting whether or not it's, a little bit of chance of rain today and what my high temperature is. No, I want my AI and ML method to actually include protection of self and property, and that I trust it in all situations. So this brings me to my list of grand challenges, and I was trying to put a graphic on this list, and I found this lovely set of weather-related grand challenges from the World Climate Research Program. So I put them on the side, although I'm focusing mostly on trust. These are the questions I'd like us to think about for the 5 to 10 year timeframe. How do we develop AI that is trusted by a wide variety of end users? It can't just be trusted by the scientists. It has to be trusted by the general public, and we have to figure out what it is that is different. How do we measure trust by the end users? And I'm going to talk a little bit about that in what we're doing in our AI Institute. As I said, the second part of this is largely going to be about our AI Institute, but we're not solving all of these. We're trying to solve a lot of them, but we're not going to solve all of them. All of them are altogether a very large set of questions. So we need to be able to measure trust, and we need to be able to measure trust as a function of the end user needs. As I said, the general public differs from the scientific end users, from forecasters, from emergency managers, from firefighters, et cetera. Everybody has different needs, and we need to be able to measure the trust and know how the trust differs as a function of their needs. We need to figure out why an AI model is trusted in some situations and why it's not trusted in others. And then I think this next one is a really interesting self-aware question. And I'm not necessarily suggesting that the AI model is self-aware, but it would be really nice if the AI model would know itself that it should not be trusted in certain situations. So let's say there's a particular weather regime that doesn't work all that well for the AI model. It would be nice if the AI model said, I don't think you should trust my predictions today. Like the setup today just isn't fitting what I've been trained on. It's outside of my experience. Here's my prediction, but I'm really low confidence in it. And likewise, there should be another day where it says, this is perfect. This fits into everything I did, and I think you should trust me today. And then we would like it for it to know when it's trusted, and for the human to trust that this is getting a little circular, but the human to know that it should trust that the AI model trusts itself. And then finally, how do we use our understanding of trust to improve our AI methods? Because all of this, if we've defined what trust is and we've got our grant, we're understanding what trust really means, we need to take that back and actually make our AI methods better. And then this isn't intended to be a final question, but it is something that is currently a very hot topic, and certainly something we're doing at our NSFAI Institute, which is how does explainability and interpretability affect trust? And we're primarily looking at that for the scientific end users, but I'm very much interested in it in all end users, because I think this question particularly gets to the how do you measure trust with the different function of the different kinds of end users. I think that the scientific end users want something completely different out of the explainability and interpretability than the general public does. And the general public, for example, and I'm not making this in a general sense, but I'm going to just flat out say I suspect that most of them don't want to look at a saliency map, for example, whereas the scientific end users probably do. And maybe saliency maps are not the best thing in the universe. They're just an example that came to mind. I think if you gave a saliency map to most people and you said, this is why you should trust my AI, they'd look at you funny. Whereas we can do better. How do we explain it and interpret it in a way that will work for all end users? So with all of that said, I'm going to jump into giving a summary of what we're doing in our NSFAI Institute. So I am the director for the NSFAI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography. This slide is getting more and more crowded as we add more and more partners, but we have all of the academic partners listed down the right-hand side. We recently added an academic partner. We have a whole bunch of private industry partners who are also on the lower left-hand corner, and then government partners that we're working with NOAA. We would love to figure out how we can work with DOE. We're working with an NCAR as well, federally funded research lab. And our goal is that we are going to uniquely benefit humanity by developing novel, physically based AI techniques that are demonstrated to be trustworthy and directly improve prediction, understanding, and communication of high impact environmental hazards. Feel free to go follow us on Twitter. I'm mostly the one who tweets, so it's not a huge amount of tweets, but go follow us. We try to tweet about our research as well. I'm going to just give a brief, because I know I only have 15 minutes, brief overview of what we do. We have four focuses to our research: the foundational research in trustworthy AI and machine learning, the use-inspired research in environmental science, and the foundational research in risk communication for the environmental science hazards. And those three together form our main research cycle. And then I strongly care about broadening participation in workforce development, and that is our fourth focus. And then all together, that makes up our institute. And I know that yesterday were talking about broadening participation, and so I actually included a slide on it, even though this seems like it's mostly a research talk. I really think it matters. We need to continue to improve our broadening participation activities at all levels. So focusing first on the research, and because I knew I didn't have a whole lot of time, I am sticking with very overview slides. The foundational research in trustworthy AI and machine learning, we have three goals for what we're doing. We've been in existence for about a year. If you want to hear more about sort of updates on this, we're working on updates for our webpage, and I also have a bunch of talks I've given recently, and they've been recorded, and so they're available online. So I'm just for this talk giving goals. Our three goals are that we are developing explainable AI methods aligned with environmental science domain perspectives and priorities. And what does that mean? It means that generally speaking, the XAI methods that exist right now are focused on creating XAI for images. What part of the bird picture that you looked at was important to tell you that it was a bird? Was it the beak? Was it the eye? What was the shape? That isn't necessarily how environmental science data looks. There's a high degree of spatial and temporal autocorrelation, for example, and we need to be able to change our methods to understand, to deal with what environmental science data really looks like. We're looking at developing physically based AI techniques, which is related to the previous goal, because the explainable AI methods caring about the environmental science data need to care about the laws of physics. And then finally, we are developing robust techniques. And I know that we talked about that yesterday in the sessions as well, that we need to be able to be robust both theoretically and empirically. We need to understand that weather provides its own adversary, and we need to be able to handle learning under adversarial data conditions and being able to give predictions that are robust. We have 5 application domains. Our 5 application domains, again, I'm just going quickly through these. So we have convective weather and winter weather, but our 2 goals before I get to the other 3 in a second, we want for all of the application domains to use the trustworthy AI to provide actionable information to a diverse set of end users and enhance our scientific and physical understanding of the basic processes. So we're not just trying to improve forecasts, we're trying to improve our understanding. We're looking at convective weather, we're looking at tornadoes, wind, hail, lightning, all the convective hazards. We've been recent work looking at some nowcasting of all of these. Winter weather, a variety of hazards, including snowfall prediction, icing, visibility, all sorts of things. There's some fun stuff just starting up in there. Tropical cyclones, trying to improve our understanding of the formation of tropical cyclones. S2S, particularly looking at the focus on extreme weather. So things like the atmospheric river that's happening right now. Can we predict some of that about 2 weeks to 3 weeks out? 3 minutes. Oh man, I got to go faster. Coastal oceanography is our final one. And so looking at harmful algal blooms and coastal flooding, et cetera. I have a final slide that's a big slide, so I want to make sure I get there. I'm just going to go really quickly. The foundational research in risk communication really, really matters to what we're doing at our NSF Institute, because we care about what it means to have trust. And that is what I talked about at the beginning. So with that, I will go very quickly and say that the risk communication work that we're doing, we're just beginning interviews of actual scientific end users and understanding what it is they perceive about AI, and specifically for forecasting, why they think something is reliable or trustworthy. And so there's a quote down here. The first word that comes to mind is reliability. It's almost like a verification. Is it reliable in this situation? Is it reliable in my part of the domain? We'll have lots more results to come. Because I know Scott's going to tell me 1 minute in a second. our education and workforce development, I said this was really, really critically important. I want to push, oh my goodness, this looked fine last night. The formatting's wrong. We have a AI certificate, and I'm sorry about the formatting. It looked beautiful last night. They have an AI certificate at a community college. It is one of the first community college AI certificates approved in the US, and it is starting this semester. And we will be taking it nationwide. And it's a Hispanic serving and minority serving institution. So if you're interested in learning more about it, talk to me. And I want to make, before I get to my very final slide, I want to make a final push to say that this workshop is great, because what we really need to solve the resiliency of humanity to climate change is a multi-agency, multi-sector approach. And I really want to help be a part of creating that. So I just talked about our NSFAI Institute. I also talked about the grand challenges and trust, but I think we really need to have our agencies working together. And I'm really glad that that question was asked yesterday as well. And we also need to talk about international partnerships. And in my final minute, my last slide, I wanted to wait till the end because I knew more people would be here at the end. I have another job that is very related to everything that is happening. I am the editor-in-chief for a brand new journal that AMS is hosting. It is the Artificial Intelligence for the Earth Systems Journal. And as of this morning, we are taking submissions. We are open for submissions. And I have our topics that are here. You can go to the website and you can go submit. And we are super excited to have your submissions. And I want to say one last thing. One of the things that this journal is going to do for everybody across all of the fields is push the development of AI and machine learning, because we are not just publishing applications, but also publishing the methods. So we are really the development and the application of the methods. And then please pay attention to my last bullet on there. We also care about societal applications, including ethical and responsible use of AI and ML. And that is it. I suspect I ended on time.
Congratulations, Amy. And for all of you involved, that's a big step. Scott, you're on mute.
Thank you, Amy. Over to you, Forrest. Much appreciated, Amy.
Okay, thanks, Scott, and thanks everyone for coming this morning and attending. Our next 15-minute presentation will be given by Professor Pierre Gentine. He's the Maurice Ewing and J. Lamar Wartel Professor of Geophysics in the Department of Earth and Environmental Engineering and Professor of Earth and Environmental Sciences at Columbia University. He received his undergraduate degree in Applied Mathematics in Toulouse, France, and obtained a master's in 2006 and a PhD in 2010 from MIT in Civil and Environmental Engineering. Pierre investigates continental global scale hydrology with big data, process models, and machine learning techniques, particularly in a context of a warming climate under rising atmospheric CO2 levels. And very relevant to the group gathered here today, Pierre is also the director of the new NSF Science and Technology Center called LEAP, Learning the Earth with Artificial Intelligence and Physics. And I'm sure he'll speak quite a bit about that today. Take it away, Pierre.
Thanks a lot, Forrest, for the introduction, and thanks a lot for the invitation. So today, also based on what Nikki were asking us, so I was trying to get to share what is actually exciting these days, where we actually see a lot of potential benefit and a lot of excitement, especially as part of this new center. And so it's going to be really looking at climate modeling and what is the potential of AI for climate modeling. And I should mention that this STC is actually a collaboration between Columbia, NYU, University of Minnesota, UC Irvine, and Teachers College. And that's called LEAP, again, Learning the Earth with Artificial Intelligence and Physics. So when we, kind of the background for that is when we look at climate models, the unfortunate truth, even though there was this recent Nobel Prize in Physics for climate modeling, they are still way too uncertain for many of the applications that we want, especially for climate adaptation. And if we look across different models, there's still very substantial spread in terms of trying to predict even basic things such as global temperature for a given amount of greenhouse gas concentration. And that's really a main roadblock for the community because it limits basically mitigation strategy and also basically adaptation strategies. And it's increasing basically the cost associated with all of that. And when we start thinking about all of that variability and the spread we are seeing across those different models, we can actually relate that back to very small scale processes such as clouds or ocean currents. And I'm sure Loredana is going to talk a lot more about that in a few weeks, so stay tuned. But those small scale processes are very, very important for the global scale response. And they are very uncertain, and we need to actually do a better job at representing that. So the way we represent a physical or biological process is through what we call a parametrization. So that's a physical process or biological process that we are trying to represent, such as clouds again. And what we are trying to do is trying to represent that at the scale of a climate model, which tends to be relatively coarse, on the order of like 100 kilometers or so. And really what we are trying to do is we are trying to say, what is going to be the impact of that particular process at the scale that we can resolve. So if we think about some variable, it could be temperature or something else, we take the average over some coarse scale domain, which is basically the grid size of the climate model. And we would want to know what is the collective impact of, say, clouds or convection or ocean eddies onto the grid mean, and because they are interactions, the small scale has an important impact on the large scale. However, historically, what's been happening is that people base those parameterizations based on physical intuition, but a lot of that at the end of the day boils down to empiricism. So there's a lot of empirical relationships, and there's actually a huge amount of structural errors and structural biases in the way we actually build those parameterizations. And in fact, a lot of that basically explains the intermodal spread I just showed you before, especially for climate projection. And again, temperature is one example. If we could go to rainfall, which could be even worse. And when you start zooming in to a particular region at the regional scale, the diversity is actually even larger, which is the main roadblock, again, for the community for adaptation and mitigation. So what we thought a few years back, actually, with Mike Richard, is that we could think about maybe using high resolution simulations, because a lot of them can actually resolve many of those biases that we have in large scale simulations. And because they alleviate some of those biases, we can maybe harvest the data and try to learn the salient features of, say, convection or clouds at the scale, at a scale similar to a climate model. So in that case, what we are doing is we are trying not to build a physical parameterization, but instead trying to do a data-driven type of approach. So it was more of a proof of concept at the time, but then that started quite a bit of work in that direction. And basically the idea is you take the fine scale simulation and you constrain that to a scale, again, that's similar to the climate model. And then what you do, you pass that through your favorite algorithm, could be, and we have a zoo of them, it could be a neural network, convolutional neural network, or random forest. Different groups have used different things. And you take basically the core scale resolution field for like temperature, moisture, or humidity, and some fluxes at the bottom. And you want to predict, again, the tendencies in terms of temperature or humidity in that case, so the heating and the moistening due to that, in that particular case, to convection. And when you compare, so that's a bit fast, sorry about that, but at the top is going to be the cloud resolving model. So the model that's relatively trustworthy at roughly a kilometer scale, 2 kilometers in that case. And the comparison to a neural network at the core scale resolution that's trying to reproduce the cloud resolving model. And what you can see is that the main features of convection in terms of the moistening on the left-hand side and the heating on the right-hand side are very well reproduced by the neural network, capturing a lot of the spatial and temporal variability that we have in the original high resolution simulation. You could actually couple that online. So that's what we've done over the last couple of years. You can directly couple that within the model, and you could compare statistics such as extremes and precipitation. It does a very good job, actually, surprisingly. So that we were very hopeful. We thought, okay, that could be a way forward and could actually kind of go against the deadlock that we have in the physical parameterization space. One question, though, is how is that going to generalize to unforeseen conditions? And climate change, we know, is a shift in the distribution. So it's a primary question and very unusual for the typical machine learning algorithms, which are great at interpolating, but not very great at extrapolating. The other issue is related to physical constraints. So when we have a climate model, it's actually critical to get energy and mass conservation. In fact, when we think about climate change, we are dealing with very few watts per square meter of imbalance at the top of the atmosphere. So there's no way we can get any type of imbalance within our architecture. So we need to impose strictly the energy and mass conservation. And when we checked in the neural network results that I showed you earlier, we saw that there was almost a closure of the energy and mass balance because we were close to this 1-to-1 line. But you can see that individual samples can actually deviate very substantially. Here, we're talking about 200 watts per square meter. So that's a major imbalance at a given point in terms of the energy balance. So that's a complete no-no for any type of application to climate change. The second issue is related to generalization. So the question is, when you're training your algorithm on historical data, could be a simulation, but it could also be some remote sensing data, for instance. how good of a job will you be doing moving forward into the future? And so we played a game where we try to say, okay, let's train the model in historical data, and let's warm the Earth by the few Kelvin by 1 degree at a time. And that's basically the results at the top of the cloud resolving simulation. So you can see the expansion here and the warming here at the bottom, at the equator. And you can see that when you're training just based on historical data and then trying to couple the neural network with the climate model, we're actually completely failing in that extrapolation mode. So to us, again, that was a big no-no, saying that, again, those algorithms are not great at extrapolating. They can reproduce things they've seen in the past, but that's a major roadblock that we need to address and take up from. So basically, quick summary of the issues with typical machine learning type of approach. They first do not respect physical laws. And second, they have a really hard time actually extrapolating. So this out of sample prediction is really a nightmare for them, but they are amazing when you stay within the range of the prediction. Okay, so they are actually fixes to that, so to some extent. So if you're interested, I refer you to the nice work of Tom Berkler, who's been actually trying to tackle those two components. And that's kind of the motivation for our center called LEAP. So the first thing is actually trying to develop novel machine learning algorithms to tackle those issues. And basically by combining machine learning with physics, because we want to embed physical understanding. There's a lot of things we know, some parts that we don't know so well. So why can't we combine both together so that we can extrapolate and generalize better? At the same time, we also want to use not just correlations, because you could have artificial correlations. You could have a predictor that's actually highly correlated with something, but it doesn't have a causal mechanism, right? So what we want is also embedding causality and causal inference as part of the algorithm. And we believe that once we have that, we will have better extrapolation, better generalization, but also as part of that, we'll have better interpretation, so that we go beyond the typical black box behavior of those algorithms. And the final hope is that by combining those novel algorithms with high resolution simulations, such as the example I showed you before, but also observations, because even those high resolution observations are quite wrong in many ways. So if you were to look at a very high resolution 1 kilometer scale global cloud resolving model, you'd be amazed at how bad it is in terms of top of the atmosphere radiation, typically, because they are typically not tuned to the observation. So we want to actually combine that. And you need to do that at scale with very large amount of data sets. And we need to combine that to create a new generation of parameterization, so physical and biological parameterization that can make their way into the next generation of models. In our case, the target is going to be the open source community Earth System model, the CSM. And the hope is that at the end, we'll get more accurate climate projections moving forward, because we've reduced a lot of those uncertainties related to parameterization. I wanted to maybe step back here and explain a little bit what are the type of errors we are trying to address. So when we start thinking of the errors that we will typically have in a climate model, we will have errors related to initial conditions, very important for weather forecasting. We'll have parameter issues, so parameter errors, so which are also some issues in the weather forecasting community, but they are typically taken into account using data assimilation. So we can, by assimilating a lot of observations very frequently, even if the model structure is not that great, we can do a very good job because of the assimilation of the data. So that's doing a very good job, and that's been revolutionizing weather forecasting for a long time. However, we can't directly do that for climate simulations and for climate projections, because the initial conditions are much less relevant in that case. What's going to be much more important is going to be the boundary conditions and the structural errors of the model. We are trying to mimic reality by simplified equations, and those equations can be quite wrong, and we need to actually correct that. So that's where we hope that by developing those new algorithms, we can actually correct those structural errors, but also bringing the observations together so that we can get and solve those structural errors, but also constraining the uncertainties better. And so just wanted to talk very quickly about the opportunities as part of this new center. So our hope really is to create, again, this new type of those new algorithms. So there's a very strong data and data science component, but also bringing that together with climate science. So we want to create this new field at the interface between data science and climate science called climate data science. And the hope is really to train the next generation of and much more diverse type of scientists, because there's been huge biases in terms of the pipeline for the data scientists and also for the geosciences, which have been suffering for many, many years. There will be many opportunities for PhDs, for postdocs opportunities, but also for research experience for undergrads and also some hackathons and things that can get, hopefully, the community quite excited. So, and again, stay tuned. There will be a website up by the end of the week, hopefully, leap.columbia.edu. So I'll refer back to that, and feel free to contact me if you have any questions. So quick conclusion. So we believe that machine learning is going to be an appealing approach for climate process representation, parameterization in particular. I didn't show you, but you can also use that a lot for understanding, not just by using some sensitivities, but by trying to do a dimensional reduction, which is something we are trying to do implicitly when we build a toy model of the world. And we can actually do that. We have great examples, I believe, now showing that you can understand convection better, we can understand turbulence better. So there are ways we can actually do that and get a lot of physical understanding at the same time. There are issues for climate change related to conservation, generalization, and potentially causality. And that's really the hope that we have as part of this center, solving a lot of those issues by connecting the data scientists with the climate scientists and creating really something in terms of a hybrid type of approach, bridging between machine learning, but also physics, causality, and also bringing some of the uncertainties that are typically also not part of the typical machine learning algorithm. So with that, I'll conclude, and I'll thank you again for your insight.
Thank you very much, Pierre. I want to thank both speakers this morning, both Amy and Pierre. And we're set to go to a break now, but I want to remind everybody that we have a Slack workspace set up for questions called WS Questions. Please use that for questions that you'd like to address to either Amy or Pierre, and we'll ask them to answer them. And we will also be saving the transcript of that. Thanks, everyone, for joining the session this morning. And remember that the afternoon sessions, the first one is on land modeling that starts at 12:45. The second one that starts at 3 p.m. Eastern is on data acquisition to distribution. See you there. Thanks a lot. Bye.
Thank you, Pierre. Thank you, Amy.
Thank you.